Last video, we split a set into several groups at once, partitions and the stars and bars count. That was the last piece. In this video, we step back and see that everything in this chapter has been one question all along. Drawing K items from N, asked 4 different ways. We assemble the 4 counts into a single table and then put it to work on a famous puzzle, the birthday problem. Every earn example in this chapter draws K items from a set of N. 2 yes or no questions tell them apart. First, do we put each item back before the next draw, with replacement or without? Second, do we record the order of the draws or only which items came out? 2 binary choices make a 2x2 table, and each cell holds a count. The ordered column comes straight from the counting principle. With replacement, every one of the K draws has all N items available, so there are N to the K ordered sequences. Without replacement, the pool shrinks each time, N then N minus 1 down to N minus K plus 1, which is N factorial over N minus K factorial. The unordered column drops the order, recording only which items came out. Look along the without replacement row. Any selection of K distinct items can be arranged in K factorial ways, so the unordered count is the ordered one divided by K factorial. That is, N choose K. The with replacement row is subtler, because a repeated item cannot be reordered into distinct sequences. The stars and bars argument from last video handles it and gives N plus K minus 1 choose K. 4 cells, 2 questions. Recognizing which cell a problem lives in is usually the whole battle. Now one example that uses 2 cells of that table. A room holds K people. Each person's birthday is equally likely to be any of the 365 days of the year, with different people unrelated. What is the probability that at least 2 of them share a birthday? It is easier to count the opposite, that all K birthdays are distinct, and subtract from 1. List the birthdays in order. That is a sequence of K days drawn from 365, with repeats allowed, sampling with replacement, ordered. So there are 365 to the K equally likely outcomes in total. The outcomes with all distinct birthdays are exactly those drawn without replacement, ordered, a K permutation of 365. 365 times 364, down to 365 minus K plus 1. The probability all are distinct is the ratio of those 2 counts. So the probability of at least one shared birthday is 1 minus 365 factorial over 365 minus K factorial times 365 to the K. Now evaluate it. As the room fills, the probability of a shared birthday climbs, slowly at first, then steeply. It first passes 1/2 at just K equals 23, where it is about 0.507. In a room of only 23 people, it is already more likely than not that some pair shares a birthday, even with 365 days to go around. The surprise comes from a swap. People imagine the chance that someone shares their particular birthday, which grows far more slowly, instead of the chance that any pair matches. And that is the chapter. Every sampling problem is 2 questions, sampling with or without replacement, and sampling with or without order. The answers dictate which cell of the sampling table should be used. Next chapter, we make probability models rigorous with the axioms of probability.